Let's do a few examples here. A car is moving east and has an acceleration of 0.51 meters per second squared west. First of all, what does that mean? It was moving east, it's accelerating west. That means it's slowing down, right? Its acceleration is how its velocity is changing. So if it was moving east and its velocity is changing toward the west, that means that it's slowing down. If the mass of the car is 2,000 kilograms and the normal force between the car and the road is 17 kilonewtons, what is the coefficient of friction? So let's do a free body diagram over here. Free body diagrams are a wonderful idea in pretty well every circumstance. Your free body diagram does not need to have wheels, but even so, it will. So we know that we are given the normal force and that the force of gravity is also acting on this vehicle. It is moving east but has an acceleration west. Okay, so let's think about what forces are moving this car. So it doesn't say anything about the car trying to drive forward, right? It doesn't sound like this person is actually pressing on the gas. It sounds as though this person is either hitting the brakes in order to slow down or they've stopped pressing the gas. So we're going to assume there's no forward thrust force from the engine, okay? And so that just means that we're going to have the force of friction pulling it backwards or pulling it west. So we're not going to include a forward thrust force because it doesn't sound like there is one. So these are the three forces acting on the car. Now in this case, the force of gravity and the normal force are not going to show up in our F net because what we are concerned about is the east-west acceleration and force acting on this car. And since the normal force and the force of gravity are up and down forces, they are not going to come into play in F net. Now that does not mean that we won't need to use them somehow because they are both part of the friction formula. Okay, so that's the only reason that we'll need to be able to use them. We'll start with F net equals ma. We are told A, 0.51. We are told the mass, which is 2,000, and we are told the normal force. But we are going to find out that we really didn't need to be told the normal force. So F net equals ma. So we want to split this into the forces that are acting on this car in order to produce this acceleration. So again, this acceleration, being east-west, or being west in this case, is not affected by the force of gravity or the normal force. So we should not include those in the net force. This should only be east-west stuff going on. And the only east-west force there is the force of friction. So we put in the force of friction in F net, and that's the only thing that's there. It often feels like there should be more. I'm splitting this. That's the word I've been using. I'm splitting this into pieces, but there's only one piece. So the force of friction in this case is equal to mass times acceleration. That's all there is. Okay, now we're trying to figure out what is the coefficient of friction. That's not in this formula yet, but we should expand this force of friction into its equation. So that gives us coefficient times the normal force, that's a vector, is equal to mass times acceleration. And now we can see this is where we're going to get the coefficient of friction from. Let's do some rearranging. I'm going to divide by the normal force to get the coefficient by itself. So the coefficient is ma divided by Fn. Okay, now the question tells us the mass is 2,000. It tells us the acceleration is 0.51, and it tells us the normal force is 17,000 newtons. But let's remember that on a level surface, the force of gravity and the normal force are actually the same. And so we can replace this normal force with the force of gravity, and we know the formula for that. It's mass times 9.8. It's mass times the acceleration of gravity. So we're, in this case, going to use this 17,000 newtons. The kilonewtons over here is 1,000. So we're going to use that 17,000 newtons in the formula, but in general, you're not going to be told what the normal force is. You're going to need to remember that the force of gravity is the same as the normal force on level ground. So the coefficient is 2,000 kilograms times 0.51 meters per second squared divided by 17,000 newtons. We cannot use kilonewtons, so we can't have 17 on the bottom because the force needs to be measured in newtons to get the right units on this coefficient. There are no units on the coefficient. It needs to just cancel out the newtons on the top. So our coefficient is going to be 0.06. That's it. It's got no units on it because notice kilograms up here times meters per second squared up here gives you newtons. Kilogram meters per second squared is newtons. Divided by newtons on the bottom, you just get newtons divided by newtons, which cancels out. And so you're ending up with just a unitless number, 0.06. Now that is very slippery, we would normally say. So probably this person is not hitting the brakes at all. They are probably just coasting. And you know that you're going to slowly slow down over time. So that's probably what's happening here. A box has a coefficient of friction of 0.11. If a force of 35 newtons is needed to push it across the floor with a constant velocity, what is the mass of the box? So we're looking for mass. We are told the coefficient of friction, mu, is 0.11. We are told the applied force is 35 newtons. And we are told that this is moving at a constant velocity. Look for these words. Constant velocity. That would mean that the acceleration is 0 meters per second squared. Okay, we're looking for the mass. So at this point, I'm going to draw a free body diagram down here. So we have the force of gravity. We have the normal force. We have the pushing force. So we're going to call this the applied force. And the force of friction. Now this question doesn't say anything about the force of friction. But because we know that there's an applied force and that this is moving at a constant velocity, that means that there's no acceleration and the pushing force has to be balanced out by a force that's resisting the pushing. Okay, and so we know that there must be friction because otherwise it would just speed up in the direction of the applied force. And that doesn't happen. It's constant velocity. So we're looking for the mass. F net equals ma. Okay, here's the mass. Right there. That's what we're looking for. So now we need to put in all of the values that we know in order to get that m by itself. So acceleration is 0. This seems to be troublesome. Because if I put in a 0 for the acceleration over here, that entire side equals 0, and that means where's my m? How can I solve for m if I've just canceled that out with the 0 that's attached to it? We better expand the F net thing and maybe put in all of the equations that we're going to use before we do any canceling out like that. So F net is the applied force minus the force of friction, and that equals ma. We know the applied force is 35 newtons, so there's no expanding to do for that little piece of equation. But the force of friction, it needs to be expanded into its pieces. So Fa minus coefficient times the normal force is equal to ma. And then we also need to recognize that the normal force is the same as the force of gravity, right? I'm going to write that up here. The normal force equals the force of gravity when on level ground. Okay, and since this is a level surface, it doesn't say that, but we have to assume that because it doesn't tell us anything about the surface being angled. Then we can put in, instead of the normal force, the force of gravity formula. And the force of gravity formula is mass times 9.8, or the mass times the acceleration of gravity. So the applied force minus the coefficient times mass times 9.8 is equal to mass times acceleration. And here is where our problem disappears. We thought that by putting in the 0 for the acceleration at the beginning, we would be basically erasing the variable that we're trying to solve for. But there's actually another variable in this equation, and that's in the friction formula. So we can put in the 0 over here and cancel this guy out, because we still have an m over there. And so what we end up with then is that the applied force is equal to the force of friction, right? And that makes sense, right? Because this is constant velocity, no acceleration. That means that the horizontal forces must be equal to each other. And so we have the applied force. When I add mu mg to the other side, I get the applied force is equal to mu mg. I am told the coefficient. I know that g is 9.8, and I'm told that Fa is 35 newtons. So I can solve for the mass given all of that stuff. But let's rearrange this first to get the mass by itself. So I could have done that rearrangement in the second step over here instead of moving the entire force of friction thing to the other side, but I liked this better. So there you go. So we're going to divide by the coefficient and the acceleration of gravity. So the applied force divided by the coefficient times gravity is equal to the mass. And now we can put in all of our numbers. So we get 35 newtons divided by 0.11 times 9.8 meters per second squared is equal to the mass. Now you need to be careful that you punch this into your calculator correctly. You have to go 35 divided by, either put this whole thing in brackets or calculate this separately and then divide. But if you go 35 divided by 0.11 times 9.8, your calculator is going to do BEDMAS better than you, and so it's going to do it not how you intended. And so when we do this, we get 32 kilograms. That is the mass. And if we look at the values in the question, 2 sig figs, 2 sig figs, then our final answer is to 2 sig figs. So that is correct. And the final example, which is a pretty common one. A 50 kilogram mass is on a level surface. The coefficients of static and kinetic friction are 0.45 and 0.40 respectively. So that means static is 0.45 and kinetic is 0.40, but you should have been able to figure that out because static should always be higher than kinetic. How much force is needed to start the mass moving? So in order to start the mass moving, we said that static friction has to be overcome, right? We have to push with slightly more force than the force of static friction. But the amount of force that you need to exceed static friction by is infinitesimally small. It means any tiny amount more than the force of static friction and it will start moving. So we can just assume that that number is 0. So really what this question is asking for is how much friction do we need to overcome? Okay, that's what we're looking for. So the amount of force needed to start the mass moving then is just the force of static friction, or F sub Fs. That's what we're looking for. And we are told the mass of this object, 50 kilograms. We are told the coefficient, which is this guy, mu. The static one is the one that we need for this question, and so we're going to use 0.45. We're looking for the force of static friction. So the force of static friction is the coefficient of static friction times the normal force. Right? The force of friction is the coefficient of friction times the normal force. And in this case, since we're talking about static friction, it's the static coefficient times the normal force. Now this is a level surface. And so on every level surface, the normal force is equal to the force of gravity. That's on a level surface. We can't always assume that those two are equal, because not every surface is going to be a level surface. But in grade 11, because this is kind of an introduction to that type of thing, to force calculations, then we will just stick with level surfaces. But if you continue to grade 12 and beyond, then that assumption goes out the window. So, in that case, since the normal force is the same as the force of gravity, that means that we can use mg as the normal force. Okay? So I'm going to put in the force of gravity here because we're talking about a normal level surface, and then I'm going to replace it with mg, just to be clear. So this is Fg because of that level surface thing, and then we can expand Fg into its formula. So the force of static friction is equal to the coefficient times mass times g, which is 9.8 meters per second squared. So now we know the coefficient of static friction is 0.45, the mass is 50 kilograms, and g is 9.8 meters per second squared. So we have all the pieces that we need to calculate the force of static friction. So Fs is equal to 0.45 times 50 kilograms times 9.8 meters per second squared. And from that, we get 220.5 newtons. And that's going to be backwards because that's friction, but what we're actually looking for is how much force is needed to start the mass moving. And so the last thing that we should say is that the force of static friction is equal to the force applied. Basically, the applied force should be slightly larger, but the amount larger that it needs to be is so small that there's no need to write it down. Okay, so we're not going to bother with that. Every time that you see that how much force is needed to start it moving, what you're really looking for is the force of static friction. Okay, and so this is what we're looking for. Now, this has too many decimal places for significant figures. So if we look at the question, this has 3 sig figs, this has 3 sig figs, and this has 3 sig figs. And so we should round this to 3 significant figures. So this would be 221 newtons. And I'm going to write SF, sig figs, on the side, just so we know what we're talking about there. Then, once it is moving, so we've applied this force, the 220.5 newtons, to start it moving. If we continue to apply the same force, what is the acceleration? So, what happens once it starts moving is that the coefficient of friction switches to kinetic friction instead of static friction. And so the amount of friction that's being applied to this mass has gone down from when it was not moving. Okay, and so what has changed is the force of friction is now kinetic instead of static. This is what is new. And so what we're going to need to do to figure out the acceleration here is use F net equals ma. Okay, acceleration, that's where we get it from when we're talking about force. So in this case, we don't have any other information other than our applied force is 220.5 newtons. And yes, I'm going to use that number rather than my 221 because I don't want to use rounded numbers in my calculations. Sig figs it only applies to the very end answer. So this is the one piece that's new. Well, as well as the coefficient of kinetic friction now is 0.40 instead of 0.45. Okay, so now we're going to calculate F net equals MA. Okay, now in F net we have two pieces. We have two forces that are occurring. We have the applied force, that 220.5 that you're pushing with, and we have the force of kinetic friction, which is trying to hold it back. We should not include gravity or the normal force in F net because those are both vertical forces, right? And we are just dealing with horizontal forces here. This acceleration over here is a horizontal acceleration, not a vertical one, and so we should only have horizontal forces. Okay? So we're going to split F net into its pieces, which would be the pushing force or the applied force and the force of friction. Now I'm going to make the force of friction negative because it is backwards. And it's kinetic, so I'm just going to put the K down there. Equals MA. I'm trying to solve for the acceleration. So I'm going to rearrange this. Then I'm going to expand the friction formula into its pieces. Okay, that order is not specific. If you would like to, you can expand this into its pieces first and then do the rearrangement. It makes no difference. This time I'm going to choose to do it this way. A different time, I'll do it a different way. So I'm dividing by m. So I get FA minus FFK divided by m is equal to the acceleration. Now let's just check what numbers I can put in here already. I know the applied force is 220.5. I don't know what the force of kinetic friction is, so I can't plug that number in. I'll have to expand that piece. And I do know the mass is 50 kilograms as well. Okay, and so what I need to figure out is what number to put in the force of kinetic friction over there. Just like before, I can expand that. Here, I'll put it up here. The force of kinetic friction is the coefficient times the normal force. And in this case, the normal force is exactly the same idea as before. Because it's a level surface, it's the same as the force of gravity. And so we can just use this whole thing right away. We already did that expansion work in part A, so we don't need to show that expansion again necessarily in part B. We're just bringing in the same idea we used before. So we have FA minus mu K mg divided by m equals the acceleration. And now these are all numbers we can plug in. We have the FA, we have the coefficient of kinetic friction, we have the mass, we have 9.8 for gravity, and we have the mass again. Now remember, I can't just cancel out the mass from the bottom and from the friction term because there is no mass in the FA. Right? So I can only cancel out the mass if I can divide each term by the mass. And I can't do that here. So we can plug in all our numbers. 220.5 newtons minus 0.4 times 50 kilograms times 9.8 meters per second squared. I'm going to go upwards so I don't get in the way of my face. Divided by 50 kilograms. That's the whole thing. And that's all equal to the acceleration. Okay, and what I end up with is an acceleration of 0.49 meters per second squared. That's an a vector, and so I should have a direction on it as well. And so it doesn't tell us anything about specific directions like east or west or north or south, and so we are just going to say forward. Because if I'm pushing it, I'm presumably pushing it forward, and friction is trying to hold it back. So there's our acceleration.